Okay, so now we're going to talk about the inverse optics problem. So the idea here is inverse optics refers to the task of reconstructing the 3D world from two-dimensional retinal images. The problem arises because there is an infinite number of possible physical scenes that could give rise to the same 2D projection on the retina. And this means that there's no unique situation or solution. When an image is formed on the retina, much of the information about the original three-dimensional scene is lost. This depth information is reduced to a two-dimensional plane, and aspects like lighting, texture, and motion can further complicate how objects are represented by the visual system or perceptual system. As a result, computing an exact inverse solution requires knowledge that is not available in the retinal image itself, right? So in mathematical terms, inverse optics is an underdetermined problem. The number of unknowns, unknown variables, 3D properties, such as 3D properties of objects, their position, size, etc., far exceeds the number of known variables that we get from the two-dimensional projection. So this makes it impossible to solve directly without additional constraints or assumptions. And here are some examples of um, the inverse optics. Usually it doesn't really matter. We're pretty good. We probably don't even realize that there's ambiguity because we are so efficient. We have such efficient perceptual systems, but sometimes it messes with us, right? These heuristics can fool us, right? So, isn't it on the left is a picture of a snail, what appears to be a snail, going up onto a bench and approaching a lady, right? And the other one is a picture of a woman who appears to be very, very small, and she's sitting on a chair, and her husband is doing something that doesn't make any sense. Okay, and but it notice how, right, like that's not really what it is, right? If you look at the snail from any other angle, this is you might see something like, or from this angle, you'll see something like this. It'll become clear that it's not what it appears to be. And same here, right? It's sort of a perceptual illusion that works because of the heuristics of the perceptual system. And so we can talk about something more simple, right? So in this example, right, what you see, what hits your retina is a penny, occluding what appears to be a slightly smaller penny. And you likely do not perceive the farther penny as actually being smaller because of three reasons. One, pennies usually don't vary in size, not this much at least. But more importantly, things get smaller the farther away they get from us, and also the farther away penny is occluded by the other one, which suggests that that penny's farther away. Therefore, you probably perceive this as two pennies of the same size, with the closer one or the larger one, including the farther one, and the farther one is just simply a little bit smaller because it's farther away. However, there are an infinite number of ways to perceive this. It could be that the penny is actually the penny that is farther away is actually much larger, but because it is much farther, it appears slightly smaller. It could also be that the penny that is farther away isn't a full penny, but there's like a bite taken out of it, and that the closer penny isn't actually occluding any part of the farther penny. Um, so yeah, a small object nearby can produce the same image on the retina as a large object farther away. Occlusion causes parts of the 3D scene to be hidden, which introduces more uncertainty. And here's another version. I'm just talking about more of these. So here's a Necker cube, right? And this is probably the most dominant interpretation, but there's also another interpretation that's less dominant, which is that this dark square is slightly closer to you and it's angled up, right? Those are like the most likely interpretations, but You could also have this interpretation, which is that that there's like a number of like sort of disjointed pieces that come together and make it look like a Necker cube. So the point is that many interpretations are possible, but only some are actually considered. So similar to the likelihood principle, which we didn't talk about, but just means likelihood principle just means that you pick the thing that's most likely. Well, our system picks the simplest perception because it's more likely. Here's another one. So here's, you probably look at this and think it's, four squares of different colors, equal size on a page, on a piece of paper, right? Or whatever, at the same distance. But in reality, it could be this, right? It could be that that the squares vary in size and distance and even angle, right? But you still get the same perception. And so one thing that you should know, so this is a possible interpretation. It's unlikely. And the reason it's unlikely is because in order to perceive this information, or one reason why it's unlikely is because in order to perceive this information this way, you need to view it from a very precise viewpoint. We call this an accidental viewpoint. And the visual system knows that implicitly knows that this is a possibility, but ignores it, right? And so basically the heuristic is to disregard perceptions that are only possible from one viewpoint. Um, I guess we'll talk about a few more. So another sort of thing that we use, right, is what's called environmental regularities. I don't know if we've discussed this, but our knowledge of the environment plays an important role in perception, right? If the environment is relatively static and there are regularities in the environment, we should use these to our benefit to sort of constrain our perceptions. Like certain characteristics tend to be predictable because they occur frequently, like blue skies are often blue, at least during the day, or gray maybe, but vegetation's green and buildings usually have vertical and horizontal lines. These frequently occurring characteristics are known as regularities of the environment, physical or environmental regularities. So, yeah, they're physical regularities are regularly occurring physical properties of the environment. And experience with these physical properties molds our perceptual system. And one of these is called the light from above assumption. So we usually assume that light is coming from above because why? Because it usually is, right? The sun's above us and lights are often above us, right? So here's an example. Here's you probably view the circles that are lining in are like inside the square, other than the middle one. You probably view those as being bumps, right? And you probably view all the other ones as being indentations, right? But if we flip this, now it's probably reversed, right? So now you see the same circles that you thought were bumps, now you probably see them as indentations, right? And the other ones look like bumps now. And the reason is because of the sun. If you assume that the sun is from above, then the sun will hit the top of the circle. If it's a bump, and if it's an indentation, it'll hit the bottom of the circle. Same with here is just another example, right? You probably view these as footprints or indentations in sand. If we flip it, you likely maybe see it as bumps, though I don't really see it. But the idea here is that, again, because when light comes from above, when it's indented, the light hits the bottom of the circle and then there's a shadow at the top. Whereas when it's a bump, the light hits the top of the circle, and there's a shadow on the bump or on the bottom of the bump. Let's do a few more. Another thing that we talk about, again, we're trying to figure out depth. Depth is important, and it's something that we don't get to know. We don't really notice it very well, or we can't get it from the two-dimensional image. So there's the question is, how do we perceive depth? Another way we perceive depth is through what we call monocular cues. So if you had one eye, you could still perceive depth with using these cues. So aerial perspective is just that things that are farther away are going to be more faded because of the air molecules in the environment. Linear perspective is that two parallel lines are going to converge the farther they get away, farther away they get. Occlusion, things that are occluded are going to be farther away than things that are not occluded. Texture gradient is where the texture appears less apparent the further it goes into the distance. So you can tell the texture over here that's closer to you, but the farther you get away, the more less apparent the less apparent the texture gets. And then curvilinear perspective is when at the outer extremes of a visual field, parallel lines become curved, right? And which means that the farther, I believe, the farther away you are, the more curved they get. This is also popular in like hip hop, 90s hip hop music videos, right? Anyways. All right, another thing that's used, this is if you had one eye, and if you have two eyes, you can use monocular cube, or sorry, sorry, I'm getting ahead of myself. We still have one more monocular cube. So the other monocular cube is called motion parallax. So if you're looking at this image right here, notice how these buildings that are darker, because this is also taking into account the what's it called, the aerial perspective, right? There's less air molecules, right? So, but that's an aside. But notice how as you move, right, as these buildings move, the darker, closer ones that you probably think are closer are moving faster than the buildings that are farther away. And so I'm gonna, hopefully I can pause this. No, I can't pause it. I'm sorry. But here's the idea. Like, so if you were looking, if you were on like a train, for example, and the train's going this way, and you looked outside the window right here, you would see that the flower is here, the cow's here, and then the tree's here, right? And if you moved the same one just some distance, now the flower has gone from the right part of the screen or right part of your view to the left part whereas the cows moved less and the tree has moved even less. And so the things that move less are the things that are farther away. Okay, one last one. We'll talk about binocular cues. So this is a binocular cue. If you have two eyes, you can perceive depth using this, and it's called retinal disparities. So retinal just means your eye, and disparity means differences, right? So we talk about racial disparities, gender disparities. That just means differences. It's differences in the retina, what your retina sees. So objects that are appear on different parts of the retina in each eye. So right, like sorry. So look how the rose is kind of close. Well, on this eye, on the right eye, it appears way over here, whereas on the left eye, it appears on the opposite end. So there's a huge retinal disparity when objects are closer. Whereas if you look at the tree that is farther away, you'll see that it doesn't, the disparity is less. There's less disparity. So less disparity means more depth. Okay, sorry that was a little longer. We'll talk about one last thing. Yeah, let's just talk about one more. So the other thing is called the Gestalt laws of perceptual organization. These are other sort of rules that are laws, I guess, that we use to organize and understand what we're seeing, right? So one's called good continuation, points that result in straight or smooth curved lines when connected probably belong to the same object, right? We would assume that this line, right, is the same and it doesn't just stop here, right? The other one's called Pragnans. I think it's German, but it just means good figure or simplicity. It means every stimulus pattern should be perceived in a way that would yield the simplest structure possible. So here we perceive these as 5 rings, and 3 of them are occluded by 2 of them, but it could be that there's actually 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces, right? That when you combine it, it looks like that. Another one is similarity. So similar things appear to be grouped together. So group things that are similar to each other. So here, if these were red, well, if we'd made every other line blue, or every other line of dots blue, we would probably group those blue lines together and those blue circles together and those red lines together. Another one is called familiarity. So things that form a law of familiarity. So things that form patterns um, that are familiar and meaningful are likely to be grouped together. So if you look at this picture, right, you may realize that it looks like there's maybe a dog there, and indeed, that's usually what people think. Okay, sorry, that was a little longer than I expected. We'll talk about problem solving now in the next video.